My goal here is to help you develop some skills for understanding light limitation and interpreting um, data that's trying to demonstrate it to you. So uh, all plants have variable light requirements. Some have more shade tolerance than others, and you can understand and compare or gauge the amount of shade tolerance by examining plant responses to different levels of light. So rapid light saturation of photosynthesis is typically something that happens in shade-tolerant species. So what we got here is 3 hypothetical species, and they each have different shade tolerance. The first species has the steepest light saturation curve. Means that what this is saying is that it's reaching its relatively highest level of growth at the lowest levels of light. That's an indication of shade tolerance. Now comparing this with these other species, such as this hypothetical species 2 that has the most gentle curve here, light saturation curve, and species 3 is in the middle. The second species here, because it takes a long time for it to maximize its photosynthetic capacity, it is, and in fact, its relative growth is much lower than the other 2 species at the lower end of the light saturation curves. That is a species that we would think one would expect it to be better adapted to a high light environment. And there's a lot of stuff that falls in between. So, the species 3 here is just put there in the center, but one can imagine a whole range of light saturation curves when you look across the biodiversity of trees across the earth. This figure is misleading in one way, and that's that all of the light, the growth maximizes at the same level. In reality, trees don't do this. Different trees have different peak levels of growth. In particular, shade tolerance, I don't want you to misunderstand. Shade tolerance is oftentimes a trade-off. High shade tolerance is great for growing in low light, but because it saturates quickly, those plants typically cannot exploit high light environments as well as shade intolerant species. So that's how they both exist. High light environments favor shade intolerant species and vice versa for dark environments. And you can see this in the Bigelow and Canham paper in particular. The species that are shade intolerant, such as red maple and white ash, they saturate not only at the high levels of light, but they actually have overall higher rates of photosynthesis at high light compared to the shade tolerant species such as beech and hemlock. And this is important when you look across forest ecosystems. There's just a range of conditions that one sees, such as high light environments, but even within them, some of this environment that I'm showing here has a lot of light and some of it has less light. So there's even, shade tolerance can help even here, but as I say, there's a trade-off. And then when one looks at dark environments like our productive mid-elevation forests in the Sierra Nevada or redwood forests, one sees high levels of productivity because the soils are pretty good and there's water is relatively available. And that means that there's a lot of productivity, there's a lot of competition for light, and having shade tolerance can help individual species persist and thrive.